So we're looking at the series sigma of n e minus n squared from 1 to infinity. So this is a beautiful application of the integral test because it's a little bit more technical to be able to prove that this series is convergent using different arguments like the basic comparison test, for example. Okay, but here if we consider the function, so f of x equal x e minus x squared, then a simple integration by substitution will give us that the integral of f of x dx, okay, is equal to, by putting u equal minus x squared, so it's equal to minus 1 half e minus x squared plus c. So this is an integration by substitution, very simple substitution. So since we know how to integrate, this will be a perfect example where we can use the integral test and connect the improper integral of f of x from 1 to infinity to the series, okay? So in order to do that, first we need to satisfy two conditions. Condition 1, our function must be positive, which is the case here because n is positive and e is positive. Condition 2, which is very important, is that f of x is decreasing. Okay? So one way to see that f of x is decreasing is to look at the derivative. So we have f of x prime, and here we use the product rule, okay? The product rule from calculus 1. This will give us e, the derivative of x1, e minus x squared, plus x time the derivative of e minus x squared, and the chain rule tells us this is minus 2x e minus x squared. So f prime of x is equal e minus x squared minus 2x squared e minus x squared, and if I factor out e minus x squared, I will get 1 minus 2x squared times e minus x squared. So clearly, for x greater than 1, okay, 1 minus 2x squared is negative, okay? So f prime of x is the product of one number which is negative and one number which is positive. Therefore, my function f of x has a negative derivative. Therefore, the function on 1 plus infinity f of x is decreasing. So condition 1 is satisfied, condition 2 is satisfied. I mean, usually another way to see that the function is decreasing is to graph it. Use any graphing utility like calculators or computers, whatever, and you just graph the function over 1 to 100, for example. And if you see, for example, that the function goes up, like in this case, from 0 to 1 over square root of 2, the function is going up. The max is 1 over square root of 2. So it goes up and then it goes down. So what happened between 1 and 10, 1 and 75 is not important. The behavior right now of the improper behavior is at plus infinity. The first block is not that important. In any case, here we're lucky because from 1 to infinity the function is decreasing. So now we know from the integral test tells us that the integral from 1 to plus infinity of f of x dx is convergent if and only if the series f of n is convergent from 1 to infinity. So here, instead of working with the series, we're going to work with the integral, again, because we know how to integrate the function. So we have the integral from 1 to plus infinity of x e minus x squared dx. This is the limit for to a goes to plus infinity, 1 to a, x e minus x squared dx. And now we use the untitled derivative. So this is minus 1 half e minus x squared between 1 and a, which gives me limit when a goes to plus infinity minus 1 half e minus a squared, and then minus minus plus 1 half e minus 1 squared is 1. So here the a squared here goes to plus infinity. We have a minus, it becomes minus infinity, and the e of minus infinity is 0. So the limit will be 0 plus 1 half e minus 1, or e minus 1 over 2, or 1 over 2e. So the limit is a finite number, therefore the improper integral is convergent, okay? Which implies that by the integral test, the series n e minus n squared from n equal 1 to infinity is convergent by the integral test. Note that the only thing I can find here is the convergence. There is no way we can connect the value of the improper integral to the value of the sum of the series. We can compare them, one is less than the other one, yes, but it's very hard to find the exact value of the series sum from the integral test. That's not possible, okay?